Hi, good morning, or good afternoon wherever you are. My name is Dwight Dunn, and this is lesson 5 of my series addressing basic differentiation technique. We're going to be looking at the product rule today, and the product rule is very useful to handle a lot of problems where the power rule is unable to. So let's get started. So right now we are able to differentiate functions looking something like that. Pretty easy. We know that this is y equal to 5 to x to the third, and we could simply multiply 3 times 5 and subtract 1 from the exponent. However, in many situations here the power rule will not work, and as such we're going to explore the product rule to do a lot of problems where the power rule doesn't work. So with this being the case right here, we got 3x minus 2x squared times 5 plus 4x. This is a typical example, as is the power rule would not be able to use, we wouldn't be able to use the power rule to actually differentiate something like this. So if we look at this carefully, we realize we got two functions here. It consists of two pieces, two separate pieces, and as a result we're multiplying those together. Now if we're required to find the derivative of this function, if I use the power rule, in a sense, a lot of students for some strange reason always take the approach to differentiate the first, then differentiate the last, and then put it as is. This is completely wrong. This is a big no-no. This is one of the biggest mistakes that most students make over the time. Now, it can get a little bit overwhelming, especially when you start to learn all the rules and know when to apply all the rules in a specific context. So as of such, we're going to take some time to address where and how the product rule is used, right? So for this situation, we couldn't use the power rule as is to differentiate that, because that would be completely wrong in terms of trying to differentiate this. So what we simply do now is we consider two functions. If I have the product of two functions, what I will have is this rule. Now let's slow it down and try to make sure that we understand this rule. What is this rule saying? This rule saying that if I have the product of fx times g of x, to differentiate something looking like this, I gonna write f of x, which is the function given first. So write that here. I differentiate the last, then I write the last, differentiate the first. Now it doesn't matter if I write this the other way, it would give me the same result. I could write g of x first, f of prime plus f of x times g of prime x. Both ways they still would be correct. So we could differentiate the first, keep the last, then write the last, then differentiate the last, write the first, or we could just write the first, differentiate the last, then the last plus the last, then differentiate the first. So that is the rule. So write the first, differentiate the last, plus the last, differentiate the first. Now this is what I tend to use a lot because it's simple and easy to follow. Now if you want to write it like this, the result is still the same, right? But for consistency and to make things move smoothly, we're going to stick to the first way of how this is written. Now with that being the case, let's go back to the problem that we just did. The problem that we have here was 3x minus 2x squared in one parentheses, which is my first function right here, and then I have 5 plus 4x. So what I would have to do, I have the first and I have the last. To differentiate, I write the first. So the first here is 3x minus 2x squared. Then I would differentiate the last. Notice I have 5 plus 4x right here in this parentheses. Differentiate 5, that's 0. Differentiate 4x, that's going to give me 4. Then what I simply would have, I put my plus, then I would write my last, which is 5 plus 4x. Then I differentiate my first. To differentiate 3x minus 2x squared, which is right here, so this is the derivative of that, I recognize that 3x, derivative of that would be 3. 2x squared would simply be negative 4x for the derivative. Now, this is how we differentiate this. So I just want to make it clear. We cannot differentiate both functions separately and then multiply them. However, we have to write the first, differentiate the last, and the last, differentiate the first. So that is the situation for the product there. Now, once I do this, I'm going to have to simplify. To simplify, I'm going to be multiplying each by 4. For simplify here, I'm going to multiply 5 times everything, and then I'm going to multiply 4x times everything. So very importantly, in terms of how to expand that. Once I expand that, I'm going to get 15 minus 20x plus 12x minus 16x. Once I complete my expansion, all I simply need to do is put my like terms together. So I have 12x right here with minus 20x, 12x. That's going to give me my 4x right there. I got negative 8x squared and negative 16x squared. That would give me my negative 24. And finally, I got my 15. So that is now my derivative. Notice this problem is very, very different from the problem from how we approach it initially, which was incorrect. Remember, we write the first, differentiate the last, plus the last, differentiate the first. Very important. All right, so let's keep it going. Let's try another example. Now, as is, I have 1 over x in the first parentheses. This 1 over x is a little bit difficult to work with as is. So to get it into a format that is more feasible and manageable to work with, I'm going to change it in something that is more workable. To do that, what we're going to do, I need to recall that 8 minus m is equal to 1 over a to m. Because I know that then, 1 over x can simply be written as x to negative 1. So from there, I'm going to use that to change my 1 over x. So to do that, I have x to negative 1 plus 1 in my first parentheses, and then I have x minus 1 in my second parentheses. So the same thing is true. To differentiate, what I'm going to do, I'm going to write my first, which is x minus 1 plus 1. Then I differentiate my last plus my last, which is x minus 1. Then I'm going to differentiate my first. So want to be very careful here. We have x to minus 1. To differentiate this little portion of the function, remember we're going to bring down my negative 1, and then I'm going to be subtracting 1 from negative 1. So that is how I end up with x to negative 2. Very importantly. Now, once I do that, what I can simply do now is expand my parentheses. To expand, I'm going to get 1 over x plus 1 minus x minus 1 over x squared. So just be careful with that. So notice right here, I want to make the transition that I can go back to 1 over x to 2, because this here going to be the same thing as 1 over x to 2. Now, once I recognize that, I'm going to have 1 over x plus 1 minus x minus 1 over x squared. So to simplify, what I'm simply going to do now is write a common denominator. To write a common denominator, I'm going to need to multiply the first expression here by x. So if I do that by x, I must do the top by x as well. Same thing is true right here. If I multiply this by x squared, I must multiply the top by x squared. So that would get the denominators to be the same. So as such, I'm going to have x right there, and then I'm going to have x squared. Now, notice now the denominator is the same. Once the denominator is the same for all of these different fractions, I can simply just operate with the top. So x plus x squared plus x minus 1 will give me x squared plus 1. So note the numerator right here is x plus x squared minus x plus 1. Don't be confused with that negative right there, because that you have to change the sign of x minus 1. So this goes, that goes. I only have x squared plus 1 divided by x squared. So that is my derivative for